Okay, you've probably heard of alchemy. Back in the Middle Ages, alchemists were trying to transform low-cost metals like lead into gold. And they did a lot of very creative things. The history of that is pretty interesting. But they were never successful, and they could never be successful because in a chemical reaction, atoms always retain their identity. You can't change another atom into an atom of gold in a chemical reaction. You can do that in a nuclear reaction, and that's called transmutation, the transformation of one element into another element. So this happens in radioactive decay of unstable nuclei, it happens in fission, and it happens in fusion. There are other nuclear reactions that can also result in transmutation, and here's a couple examples. Nitrogen-14 plus an alpha particle will make oxygen-17 and a hydrogen nuclide. Aluminum-27 plus the alpha particle gives you phosphorus-30. But these are not things that just like happen in a beaker on the counter, right? Back in the 1930s, scientists began building accelerators. These are really large buildings with the purpose of accelerating these really tiny particles to extremely high speeds so that they can bombard other nuclei with these pieces and see what happens, okay? The Joliet-Curies got the Nobel Prize in '35 for their work on nuclear transmutation. So you can have a linear accelerator. In a single-stage linear accelerator, you get a charged particle that gets accelerated in an evacuated tube by a potential difference, a voltage difference. All of this has to be done with charged particles because how else do you convince the particle to move, right? You can't just throw them. So you use voltages, and a negative particle will be attracted to the positive voltage. This is a picture of the Stanford linear accelerator. This is not a single stage, it's a multi-stage linear accelerator. And if I remember correctly, it's like a mile long. So we're taking these little tiny particles and taking multi-stages of these voltage differences and accelerating the particles faster and faster and faster. So they can get up to 90% of the speed of light, which is really, really fast. Right? So then those particles, when they collide with a target, they're very tiny, but their velocity is huge, and kinetic energy is 1/2 mv squared, right? So you've got some significant kinetic energy here. So then, they're shooting these things at targets, and then you get like showers of subatomic particles that come out. And so then, you have to figure out, well, what are these particles coming out? And I mean, it's just really kind of a crapshoot, really. You just throw it and see what happens, right? So the researchers at Stanford got the 1990 Nobel Prize for Physics when they discovered that protons and neutrons are composed of smaller particles called quarks. So, we talked about protons and neutrons and electrons, and those are the three major subatomic particles. But there are a lot of other smaller particles that make up the atom. And that's, I don't like that. This is how a multi-stage linear accelerator would work. So each of these numbers here is a different stage. And so they're going to use alternating a voltage source to attract, here they're doing protons, so it's a positive charge. And so when it gets in here, you want the far side to be negative, pulling it that way, and you want the back side to be positive, which will push it. And the timing here is really important of getting these voltage differences just right. And then here you've got your target. This is done in a vacuum because if it was done in air, your particles would be colliding with molecules in the air, nitrogen and oxygen and stuff, and they'd get stopped by that, and that would slow them down. So they pump everything out, so there's essentially nothing in there, and then the particle can move through and get accelerated. Any questions? Another type of accelerator is a cyclotron. So here we've got two semicircular halves, and we've got the alternating voltage applied back and forth. So here we've got the proton source, and the magnets are going to cause it to move in a spiral along, and the alternating voltage source is going to cause it to accelerate, to go faster and faster. So it goes faster as it goes outward. This is the Fermi National Accelerator Lab. They've got two cyclotrons in a figure 8 configuration. So here's one, and then the other one's over there. Again, accelerators for these little tiny particles in these buildings are really, really big because they just need to be super long. Okay, any questions about that?